Welcome, and thank you for taking the time to attend today's webinar, LiDAR, One Size Does Not Fit All. First, the usual housekeeping items, which I'm sure we're all familiar with by now. We will hope to take some questions at the end. We're going to do 2 polls during the webinar, and if you can fill out the exit survey on the way out, we would really appreciate it. My name is Gene Rowe. I'm the founder of LiDAR News. My background is in surveying and mapping with an emphasis on digital innovation. I will get things started by taking a brief look at what I'm calling the democratization of LiDAR. Next, Alexis Debray from Yole Development will provide his perspective on the state of the LiDAR industry. Alexis is a technology and market analyst in optoelectronics at Yole Development. As a member of the Photonics, Sensing, and Display Division, he is engaged in the development of reports as well as custom consulting projects dedicated to the imaging industry. As an author of various scientific publications and patents, Alexis graduated from NCCON and holds a PhD in applied acoustics. Alexis will be followed by Bill Colleran, the co-founder and CEO of Lumotive. He will present on scaling LiDAR to meet a range of application needs. Bill has more than 35 years of experience as an engineer, investment banker, technology entrepreneur, and business executive. Prior to co-founding Lumotive, Bill was the CEO of AnswerDash from 2015 through 2017, the CEO of Impinj from 2001 to 2014, and the CEO of Innovent Systems, developer of the world's first CMOS Bluetooth chip, which he led from inception through the company's sale to Broadcom Corporation in 2000. Dr. Colleran received his PhD from UCLA in 1993, his MS from USC in 1985, and his BS from Notre Dame in 1983, all in electrical engineering. And he has a JD from Harvard Law School, which he got in 1996. And then we'll take a few questions at the end of the session. Following a path similar to GPS, I believe over the next 5 years that LiDAR technology will become even more important in everyday life. It's following a similar adoption curve to GPS. There are more than 100 startups pursuing LiDAR innovations, with venture funding pouring into this industry, companies going public. People have found that automotive is slower to engage than they had predicted. Problems are tougher to solve. The robo-taxis are making some inroads, but there's still the whole issue of consumer resistance that's going to have to be resolved in this automotive market. Consequently, firms are pivoting into many other markets. Last week at Consumer Electronics Show, LiDAR was one of the hot technologies, from consumer electronics with LiDAR guided shower heads selling for $1,000 to what I consider to be the real game changer in this, which is the iPhone 12 Pro. Once we get Apple using LiDAR, it's going to be like GPS. It's going to be everywhere. And why is that? Well, above all else, it's an active 3D sensing technology. That really says it all. It enables the self-illumination. You're able to use it in most weather conditions. The whole issue with privacy and sensors is not an issue with LiDAR. As you'll hear from Bill, solid state is the future of LiDAR sensing. There's a lot of flexibility regarding form factors and costs. And I just wanted to make a little plug for the standards issue. From a car safety point of view, that's being pretty well covered. But from an overall data standards point of view, the industry is missing out on many opportunities by not doing a lot more with data standards. So the key market segments that you're going to hear about today, we've already mentioned a couple, the automotive, but there's industrial automation. That's a significant one. Consumer, we mentioned, IoT, the Internet of Things and edge computing, LiDAR sensors are going to have a big play in that area. A lot of us have come from AEC and BIM, so we're familiar with that market. But security and smart cities are two new giant markets to be connected into. So our first poll question, we're going to launch that. What industry, what industry or application do you see LiDAR having the most impact on over the next 5 years? So we'll give you a minute or so to fill that out. Ooh, it's looking pretty balanced. We'll give it another 10 seconds, let's say. Don't want to waste our time here too much. So we'll end the polling, share the results. And as you can see, robotics is the winner, but there's certainly plenty of interest in the other areas, with drones kind of coming in last. That is a surprise to me because I'm seeing a lot of activity in that area. Depends on the audience, I guess. So we're going to stop that there, and I will stop sharing my screen and turn it over to Alexis.
Yes, thank you. Okay, so I have to share.
There you go.
Okay. Yes, so nice to meet you, everybody. So my name is Alexis Debray. I'm from Yole Development. So we are a company. We are the headquarters is based in France, in Lyon, but we are a global company. We have analysts. We have presence everywhere in the world, and we are focusing on semiconductor market and technology analysis. And today, so I will talk about LiDAR applications and markets. So the content of my presentation is the following. So I will talk about the context of LiDAR, talk about LiDAR applications, LiDAR market forecast. I have some conclusions, and I have a few slides about our company, Yole Development. So first, the context of LiDAR. So LiDAR is using and is coming from a lot of technologies. So you can see on the left on this slide, many technologies from photonics. And also today LiDAR is present in many applications in various size, various price, and yes, it's going to be everywhere. So we can have a look at a short history of LiDAR. LiDAR is a kind of old concept. That's before the laser. Actually, the laser is a very important key component really of LiDAR. And the first applications of LiDAR were in topography. So that's one of the first application, and in space also. And then it's developed in also wind detection systems. And 2004, 2005 was a very important date for LiDAR. It was a DARPA Grand Challenge. And we have started to see LiDAR used for autonomous cars. And it was the creation of Velodyne, and a lot of things evolved from this. So LiDAR technology, I do not talk a lot about LiDAR technology here, but so it's, I would say, could be a bit complicated because there are two main routes of LiDAR. So one is 2D, it's digital photography, and the other one is laser rangefinder, so using laser to measure distances. And this give different technologies actually for LiDAR and for measuring distances and to obtain 3D images. So one is TOF cameras, which are not LiDAR, And there are mainly two kinds of LiDAR, so flash LiDAR, which are able to have an image at once, a 3D image at once, and the scanning LiDAR, which is the second type of LiDAR. Now I will talk about the LiDAR applications. So LiDAR has really evolved in many different markets now and in many different applications. So we can group in 4 different markets. So we saw that at first LiDAR also was in the space. So now it's still used in space and in defense. This is one application. The industrial application, so construction is a topography, so it's one of the legacy application of LiDAR. So it's still very important market. And energy, so wind and measuring wind for wind turbine is also a legacy application. And now we have seen many different new applications which have emerged, and still in the industrial market. So we see new applications emerging almost every day. So in logistics, in smart buildings, security, smart cities, agriculture, factory automation. Another big, so it's not a big market, but it's a big application for LiDAR is automotive. We have, and here there are 2 main applications. So I will discuss more in detail in a minute. So which is ADAS, personal cars, and also robotic cars. And recently we have seen with Apple the LiDAR being used in iPad and smartphones for AR, VR, and photography. So I will continue talking about the applications of LiDAR in smartphones. So here it's more about the 3D cameras in smartphones. So there are 2 main 3D cameras. So one is in the front and the other is in the rear. So LiDAR is mainly, today is used for the rear 3D camera. So the front 3D camera is for Face ID mainly, as the distance is something like 1 or 2 meters. And so LiDAR is not probably the best technology for the front 3D camera, but for the rear 3D camera, where we want to have a distance like 5 or 10 or even 20 meters, LiDAR is really the best technology. And today, Apple is really pushing for LiDAR in this application. And so it can be used today for having better photography or to do some augmented reality or some gaming. But probably the future will give us new applications for these rear 3D cameras in smartphones. So it's things which we'll see develop in the future. Concerning automotive applications, so there are 2 main applications for LiDAR. One is robotic cars, so also called mobility as a service. So they every company doing robotic cars or autonomous shuttles are using LiDAR today. So it's as they are using several LiDARs in each car. So it's really a key component for robotic cars. For ADAS vehicles, so the technology for autonomous driving in ADAS car or personal cars is evolving little by little. But we have seen recently, so there has been announcements last year of several car manufacturers which will use LiDAR for autonomous driving in personal cars. So this is an important trend for LiDAR as well. In the industry, so there are many different applications, and so some are already present. So we saw construction, topography, or energy and wind. And there are new applications which are emerging quite fast. This is also due to the fact that the unit price of LiDAR is decreasing dramatically recently. So it's helping it's helping the adoption of LiDAR in new applications. And so, for example, mining. So we have seen autonomous dump truck since 2008. So it's quite there is some history for this application. Also ports in China. So there is an autonomous ports since I think it's 2017. So it's already a few years ago. And there are new applications which will emerge in, for example, smart buildings, space management, or smart infrastructure. Also will be an industrial application for LiDAR. Okay, so now I can talk about the LiDAR markets. So first, I will present some the potential market for LiDAR in the smartphone application. So here we do not look at only the LiDAR, but all the 3D cameras. So there can be some other technologies. So for the front 3D camera, so probably LiDAR is high, has is too much high spec for this application. But for the real 3D camera, LiDAR is one of is the best technology and probably a very good choice. So we have here in purple the market forecast, the volume forecast for real 3D cameras, and we expect important growth in the future for this application. And so we expect for this application, so in 2035, so around $4 billion for 3D rear camera in smartphones. Here we can look a bit at the history of 3D sensing for smartphones. So there are three main technologies: structured light, time of flight, and LiDAR. So structured light and time of flight are best for 1 or 2 meters. And so structured light is used by Apple in the front 3D sensing. So it's used in Face ID. And LiDAR is probably best for the rear 3D sensing, so several meters. And so Apple has adopted LiDAR for the rear 3D sensing. And there is a lot of room for improvement for LiDAR from Apple to increase the frame rate, to increase the maximum range, increase also the resolution, the angular resolution. And probably other smartphone manufacturers will also adopt LiDAR for 3D sensing. And time of flight is easier technology, but it's not as good as LiDAR. So it has been adopted by several smartphone makers, but they will probably switch to LiDAR in the future to have better performances. We can now look at the market forecast for automotive and industrial applications. So this is the forecast for volumes. So we look at the industrial applications, the wind, the topography application, mass, so it's robotic cars and autonomous shuttle, and ADAS, which is personal cars. And this forecast is between 2019 to 2025. So we see the volume, there is a huge increase with a CAGR around 77%. And most of the volume will be driven by personal cars. So this is related to the fact that the personal car market is around 100 million cars per year. So, and there could be several LiDAR per car. So with only a few percent of adoption rate in the personal cars, we can reach several millions of LiDAR each year, which is quite an important change for the LiDAR industry. We can look also at the market forecast in dollars. So topography is a large market because the unit price of LiDAR for topography is quite expensive. So it can be up to $1 million for one LiDAR. So this makes a large market. However, for the growth for the ADAS LiDAR market will be important, and we expect it will reach $1.7 billion in 2025. So the unit price is much smaller than for topography. However, the growth is quite important, and it makes a large market for this LiDAR. And in the industry also, so the market will grow. It will not grow as importantly as for the ADAS. This is also due to a reduction in the price of the unit LiDAR. So we expect the unit price of the LiDAR to decrease. It used to be quite important, several thousand or several tens of thousands of dollars for a unit price LiDAR. We expect this price to decrease dramatically in the future, which will ease the adoption, and so the market will not grow as much as we could expect, but the volume will grow. Concerning the ADAS adoption, so there has been recently several announcements by car manufacturers. So since 2017, Audi has been implementing the LiDAR from Valeo in some of its cars. And last year, we had many announcements of car manufacturers which will implement LiDAR in some of their cars starting in 2021, this year. We expect several car manufacturers to adopt LiDAR in their cars, and it will continue in 2022 and after. So there is a good traction for LiDAR, and there could be several LiDARs in one car, so some long range, some short range. So there are also different types of LiDAR in the automotive industry, and it will expand the market. So I have a few conclusions for this. So LiDAR is really expanding into many applications in consumer, in automotive, in different industrial applications as well. So we expect the growth of the market for automotive and industrial applications to be around 19%, and a total market in 2025 reaching $3.8 billion. Yes, in 2025. So automotive and industrial will be the main drivers for LiDAR, as well as consumer. So consumer will be a very important. So there are LiDAR has a lot of key performances and will be very important technology. So we have a few reports on LiDAR. So if you're interested to know more, so we have a report on LiDAR for automotive and industrial applications. We also have a report on 3D imaging. So it goes beyond LiDAR. It's on any technologies for 3D imaging and sensing. And we also have our sister company, System Plus Consulting. So they do tear down, and they have some cost analysis. They model the cost of the LiDAR, the components, and the different parts of the LiDAR. So we have one on the Valeo Scala, one on the Livox Horizon LiDAR, which is also interesting technology, and also on the iPad LiDAR, which is the same which is used in the iPhone. So just a few words on Yole. So we cover semiconductors, also semiconductors in any application. And we have our sister company, System Plus Consulting. So they do teardowns, they do cost simulations. Okay, so thank you for your attention. And Yes, thank you.
So if you can stop sharing, Alexis.
Yes, I have to go. Sorry. Okay. Stop sharing. No. Okay.
Okay,
That's
very
it.
good.
Thank you.
So we'll go on to the second poll. I noticed some people have been typing questions into the chat. Could you please type them into the Q&A so we have them in one place? Thank you. So our second poll question, what is the biggest challenge limiting the adoption of LiDAR? Give you a few minutes to, there we go. What is the biggest challenge limiting the adoption of LiDAR? Okay. I think most people are going to be able to guess this, but but that's going to change over time. The first GPS receivers were $100,000, so there's going to be some similar kinds of adoption. We're going to end the polling in a couple of seconds. If you can get yours in, I think we're pretty steady. There was a question before about how many people have responded. This one's looking like it's about 100 people out of the crowd are responding. So we're going to end it and share results. And the big winner is cost. But I think Bill's got some good news for you there. So we'll stop sharing the results here, and we'll let Bill share his screen and provide you with the good news.
Okay. All right. There we go. Good morning, everyone. I'm Bill Colleran. As Gene mentioned, I'll be talking about some of the developments that we have at Lumotive in making LiDAR that's very scalable. That's one of the things that we focused on. And by scalable, I mean driving down the size and the cost for different applications, addressing one of the poll concerns that we just heard about. So with that, why don't I go ahead and jump in and talk about our company. As I mentioned, what we do is uniquely address a small, we call it near-range LiDAR using truly solid-state beam steering. And I'll talk about why beam steering is important. But right now, we're addressing three markets closely aligned with what Alexi talked about just a few minutes ago in smartphones, in industrial application, and in automotive. In an automotive, we break that market into two subsegments. One, the long-range LiDAR that is kind of the forward-looking LiDAR, and one that is the short-range or near-range LiDAR, and we'll talk about that as well. We have a software-enabled LiDAR, which enables unprecedented performance. We can get very granular and customized control of the steering angle and therefore optimize overall system performance. We're a 3-year-old company. We have funding from Bill Gates. And what you can see on the right-hand side are the first 3 generations of what we call our liquid crystal metasurfaces. These are the semiconductor chips that we use to steer light. You can see they're quite small there. You can also see in the lower right some renderings of our upcoming products, the M30, which is about the size of a golf ball, and the U30, which is the size of a camera module for use in smartphones. So let's jump in and talk about some of the applications. I have a slightly different spin on these. We look at 2 different segments, the long-range automotive segment, which is shown on the left. And again, that's the standard LiDAR that you've seen on the roofs of cars. That's going to be a large market, but it's also very crowded in terms of competition. It will be slower to adopt because it's life safety critical. If you look at the near-range applications, we see 3 of them. Automotive as well, but this is for LiDARs around the periphery of the vehicle so that you can sense your surroundings and do automated parking and low-speed collision avoidance and so on. You see the picture there with the children playing behind the car. That will be a very large market. Industrial, I won't go into details there, and smartphones, which Trust me, there are some very interesting applications coming out with augmented reality and smartphones. I treated myself and got myself an iPhone 12 just a few weeks ago, and I'm playing around with it, and I'm blown away by some of these applications that are enabled by LiDAR. So I encourage you, if you haven't seen some of these, go ahead and take a look around on the internet. They're pretty compelling. In any event, we see these markets being unmet by current technology, because you have to deliver LiDAR performance with a tiny and low cost device. And that's where scalability comes in. And so we think this is a compelling market. And just to expand on it a little bit, this is the automotive application. And you can see on the right-hand side, this is the forward-looking LiDAR. If you envision one LiDAR per vehicle in the year 2030, and you have 50% penetration into the 100 million cars that are sold every year or thereabouts, if that one LiDAR goes for $250, it's a $12.5 billion market. But on the left-hand side, if you look at 6 much smaller LiDARs around the periphery of the vehicle, we show them here near the taillights, near the headlights, and in the side pillar to give you 360 coverage, albeit at much lower range. If those are $50 each for the same market, you actually have a larger market, a $15 billion market for these near range LiDARs in automobiles. So this just to give you an idea of the ubiquitous nature of LiDAR that we will find in the not too distant future, and the need to make those LiDARs small, even though range isn't necessarily the end all be all in terms of performance. So why is this near range market underserved? It turns out that making LiDAR systems is most difficult when there is sunlight involved, because you have to overcome the solar background noise with the light signal that you're transmitting from the device. The way to do that is to push your optical energy into a small area so that you get high optical intensity to overcome the sunlight. But obviously, if you want a large field of view, you then have to scan that narrowly focused beam in order to get a full field of view. And that means that you require beam steering. And in today's world, existing LiDARs use mechanical beam steering, which is why you've probably seen pictures of these relatively large devices that spin round and round like lighthouses did a couple of thousand years ago. And the challenge is that that doesn't scale to get something that will fit in the palm of your hand or be the size of a camera module. So this is the big challenge for what we call scalable LiDAR, and something that our technology addresses. So in order to reach the market potential that we've been talking about this morning, LiDAR has to do a few things. It has to be tiny, it has to be cheap, and it has to be CMOS based. The last one is our conclusion based on tiny and cheap. The way to get to tiny and cheap is to ride Moore's law and the semiconductor industry. And so that leads us to the need for solid state beam steering to make it CMOS based. So here's a couple of shots of some of our early prototype devices. You can see on the left-hand side, it's what we call X for our prototype series, the X20, mounted on the roof of a car. You can see a close-up up next to a pen. It's quite small, but obviously not the size that we're ultimately going for with our small devices. You can see point clouds that can be generated with this solid-state beam steering. A still shot is on the right. I'm going to risk going over and showing a video, and hopefully this all works out. And so this is a point cloud taken from the roof of a vehicle driving around in the Seattle area where we're located. You can see the dash cam. It's taken in broad daylight, and so you can get pretty good performance. This is what I would call kind of a typical point cloud that you would see for long-range LiDARs today. Again, we're focusing now on short-range LiDAR, but just to give you a sense of the maturity of the technology and the fact that the beam steering, in fact, works. Let me go back to my presentation now. So that gives you an idea of overall system performance. The question now is, well, how do these liquid crystal metasurfaces actually work? And so I show a little cartoon here. This is one of our LCMs on the bottom. It's a semiconductor chip, and we make on that chip.
Bill,
yes.
you didn't get back to your screen, your slides.
Oh, okay. I was worried that there might be a hiccup with that, but let me do this. What do you see now?
Still seeing the same frozen point cloud image that you were showing from the video.
Okay.
You're locked in the video.
Yeah. Okay. Let me, you know what? I'll stop and start again. Thanks for giving me a heads up. I was running on my merry way. How about now?
Nothing yet. It says has started sharing.
And it seems to be locked up.
Seems to be.
Okay, give me 1 second. It still says starting to share, but there's no screen.
Yes. Now you're back to individuals.
Yeah.
I could, we could go to my backup slides.
Yeah, give it 1 second here. Try one more time. What do you see?
Started screen sharing, same thing.
And then it just stops.
Yeah.
Okay, if you could go to the backup slides, if you go to slide 8, I'll just kind of walk you through it. I don't know why, I don't know if it's a bandwidth issue on my end or what.
So what I have to do is
Keep going, keep going. Yeah. Next slide.
gosh, what happened there? Tripped me back to the other screen. I think we better go with that.
Okay. Can you go into presentation mode?
When I did that, it kicked me out.
Resume slideshow, I think.
I think we're going to have to stick with it in the side by.
Okay, so we have a chip on the bottom, which is our liquid crystal metasurface. On that structure, which is a semiconductor chip, we form optical resonators using the standard metals and dielectrics in the semiconductor manufacturing process. We then coat that chip with a thin film of liquid crystal. And when we apply electrical voltages, we can individually control the phase delay that photons experience when they encounter that resonator. And by creating a phase profile across the surface of the chip, we can cause the angle of the outgoing beam to be under our control. So the incident beam is always coming from a fixed angle. By applying different voltages, we can have the outgoing or the steered beam go into an angle that we desire. And so just like with a liquid crystal display, you apply different voltages and get a different image. In our case, we apply different voltages and we get a different steering angle. And so it's dynamic, can be controlled by software, no moving parts, has all the advantages of being solid state and scaling with CMOS and so on. So if we go to the next slide, we can see how we manufacture these. It's a standard CMOS wafer. Our manufacturing partner is Tower Semiconductor. We then use something called liquid crystal on silicon manufacturing, which is the process by which you put a film of liquid crystal on the surface of the wafer, put a cover glass on the wafer, and then dice it up into individual chips. So we've been working on this for the past several years. It's very scalable. It's very mature manufacturing technology and so on. So if we go to the next slide, we'll see what our U30 will look like. And the U30 is a U for micro, but we take all of the key elements from a LiDAR. We scale them down to be able to deliver something in the form factor of a camera module that could go into a smartphone. And the performance that we can deliver because of our beam steering is very important. We can have much lower power than what is currently used in Apple's iPhone 12 and much, much higher resolution. And a little aside here, the way the iPhone 12 LiDAR works, it is like a flash LiDAR. It illuminates, rather than the entire scene, they illuminate a few hundred dots. And that's the way that they can get that optical intensity to overcome sunlight. And then they have a standard timed imaging chip on the receive side. What we do is essentially take the equivalent of a few hundred dots and line them up into a vertical column, but then we can steer that column to get much higher resolution. Because we can do that, we get the lower power consumption and the higher resolution. So basically the idea of an iPhone 12 LiDAR but with better performance. And obviously in smartphones, power consumption is an important issue for battery life. If we go to the next slide, we'll see how this scaled technology can address other markets. In general, it's for industrial applications, short-range automotive that I described. The power can be low, the size can be much smaller. And we do all this, albeit at a much lower range on the order of 10 meters than what is typically required for the long-range automotive LiDAR. So as I said at the top, these are very distinct markets from those that are for long-range LiDAR. The next slide shows an exploded view of how the system works. You can see on the lower left is a VCSEL laser that illuminates our LCM. The LCM steers a vertical stripe across left and right or horizontally across the field of view. Reflected signals come back through the receive lens and then onto the time of flight detector to create the 3D image. And I mentioned that this is all under software control. So if we go to the next slide, you can see that we can move that vertical stripe arbitrarily under software control. So we can track an object that's moving across the field of view. We can spend more time in an area of interest to get better range, depth, and resolution in a particular area because there's activity there. We can essentially customize the behavior of the scan in order to optimize performance for the application at hand. And that's a huge advantage. And many people that we're engaged with are very excited about the software API that we're exposing that will allow them to optimize system performance using software control. So that's a unique aspect because of the solid state nature of our beam steering. If you go to the next slide, we look at our roadmap a little bit. Start first addressing the underserved small form factor markets. Those are the two on the left, the U30 and the M30. And then eventually over time, using the economies of scale from those two markets, we think we can then move into competing in the long range markets as well. We have an L30 on our roadmap that is longer range, 250 meter type of range. And the scalability holds. In other words, for the U30, we have a very small LCM, which means low cost and low power. For the L30, we would have a much larger LCM, which would be larger cost and larger power going along with the longer range that device would deliver. The unit volumes for the U30, because it's targeting at smartphones, would be in the tens or hundreds of millions of units a year. So those will drive economies of scale indeed, and that will power the cost reductions that can make us competitive in all those other markets. If we go to the next slide, you can see we have what we call an early access program that we rolled out for a number of our customers. I guess it was in the third quarter of last year. And we offered that up for people in mobile, industrial, and automotive. We signed up 7 companies that are engaging with us now to help us define our roadmap, some of the software customizations I described, and so on. So obviously not all of the logos on here are customers or have joined our early access program. 7 of them have. We can't tell you which 7, but to give you an idea, they're across all 3 of those market segments. And so folks are seeing significant advantages from our architecture and the promise of how it can fulfill their needs. If we go to slide 50, you can see a little bit more detail on the roadmap, starting from our prototype units. We had an X10 that we demonstrated at the CES trade show last January, the X20 that I showed you a photo of, and the point cloud, which caused the, the webinar to bust. But that leads through miniaturization to the M30, which will be our first volume product later this year. And that will go for industrial applications. After a period of time required for automotive qualification, that can also be sold into the near range subsegment for automotive. Further scaling will lead that in another year or so into the U30, which is targeted at smartphones. There are other applications that would be interested in that, but smartphones are obviously the big volume driver. And then using those economies of scale over time can develop the L30, which will be competitive from a cost standpoint. I mentioned an early access program that we had based on our X20. If we go to the next slide, we're introducing a similar program, which is targeted at the mini LiDAR. This is called the mini LiDAR early access program. And the idea is that we provide test data and a roadmap and customization options largely through our software API. We'll provide samples of our M20, which is a precursor to the production version, the M30, and those samples will be available in Q2. And we look to collaborate with those early access partners on customization options and so on. If you're interested in more information, you can go to our website. There you can fill out a form and get more detail and so on. And we'd be happy to have further discussions on that. So with that, I'll wrap it up. I think we have another poll and then some time for Q&A, and we'll go from there.
Great. Thanks a lot, Bill. No, we finished up with the polls, but we can move into our key takeaways. We've got a couple of slides here. Excellent job explaining that pretty important technology that you're working on. I think as people read through these here, you're going to get the same message about the automotive market getting the headlines. But as Bill has clearly demonstrated, there's a lot of other important markets out there. One size does not fit all. There's definitely new approaches to come up with the optimal combination of specs that are going to be available. He's got some very powerful flexibility built into the roadmap. Lumotive is pioneering this new solid-state CMOS approach, and we just heard about the early access program and about the opportunity to participate in that if you so desire. Just a quick kind of side note, if you will, about the Younger Geospatial Professionals Group, which is on LinkedIn. I try to support this group, and this is the future of our profession. I don't know if you're hearing about what's going on in the math and science world, but it's not good news. People are not getting into these fields, and with all the opportunity that we've seen laid out in front of us today, I think it's going to be probably the lack of people that is going to slow us down eventually here. So contacts, if you'd like to get in touch with Bill, Alexis, myself, here are the emails. We are up to 32 questions, so we're not going to get all those answered. I appreciate it. Looks like almost everyone has stayed for the entire webinar, which is just fantastic. Really appreciate your interest in all of this. So let's see if we can dig into a few questions. And okay, the first one, I guess, is going to be for me. Why is privacy not an issue? You don't get the face detail of the facial features using LiDAR. So that's my answer for why it's the benefit of LiDAR to use for crowd sourcing and monitoring and things like that. The second question, do you see the automotive industry looking to standardize the NIR reflectivity requirements for autonomous driving applications at any time soon? That sounds like one for Bill.
Sure. I see there being an attempt to do this, but the reality is that the scenes that will be encountered are too diverse. I mean, you can standardize reflectivity of road signs and so on. In fact, I think things like that are already underway. But all the other scenes are simply too difficult to control. So I think the onus will be on LiDAR manufacturers to simply improve the performance of their systems so that they can deal with the world as they encounter it rather than trying to control everything. So I see, yes, this happening, but I don't think it'll be terribly important for adoption.
Very good. We've had a couple on this issue. Will the audience have access to all of the slides? Yes, I will put a link into the follow-up emails where you'll be able to download the slides. Can you quantify in meters short range and long range? Bill?
Yeah, it depends on the application, but largely speaking, the short range applications is on the order of 10 to 20 meters, and long range is beyond that. So yeah, I guess that's kind of a working definition.
How do you see the cost versus performance versus 4D radar AIP systems? Not familiar with that.
I'm not sure what they're getting at there. I'll take a stab at this, and then Alexis maybe wants to jump in. Obviously, the longer range systems tend to be larger and cost more. The cost for a automotive LiDAR with 250 meters of range today is near $1,000, and it all depends on volume. But people are projecting that to come down to a few $100s in volume over the next several years. And for shorter range systems, the cost is correspondingly lower today. A few $100s, but coming down for smartphones to the $10 range in a few years. And I don't know what the 4D radar AIP systems is referring to.
Okay. Anything on that, Alexis?
Yeah, so the 4D radar, so they can be quite big. So in some cases, they don't really blend really in the car, and there are some aesthetic problems. And also redundancy is needed. So having electromagnetic waves and light working together is a good idea anyway. So there is some complementarity in these technologies.
Very good, thank you. Short range LiDAR for automotive can be based in ultrasound or radar. Am I correct?
Short range LiDAR competes with ultrasound and radar. Ultrasound and radar have the disadvantage that they don't have nearly the spatial resolution that LiDAR has. So LiDAR can create a much richer image of the surroundings. Ultrasound has lower range and lower resolution. Radar can have long range, but has much lower resolution. So the big win for short range LiDAR is getting the resolution so that you have a really good image of what's around the vehicle.
Very good. If the long range LiDAR is $250, why would they put $600 short range LiDARs instead of adding 2 additional long range LiDARs for $500? This is what Mobileye is doing, for example.
Yeah, so we envision in time and volume the cost of the short range LiDARs to be $50 each. So 6 of them would not be $600, they would be $300. And so the entire surround imagery would be the cost of 1 long range LiDAR. And so that's why I think it makes sense. Obviously, if the costs were the same, you would use long range. But the other advantage that the short range has, it has a much wider field of view. both horizontally and vertically. Many times the long range LiDAR has a narrow field of view, focused on the horizon plus or minus 10 degrees, and horizontally it has a lower field of view as well. So you would need to have many long range LiDARs to get the full coverage. The other issue is the long range LiDARs typically are mounted on the roof, and then you have blind spots around the apron of the car. So you need multiple LiDARs around the periphery of the vehicle to get full coverage. So the way to do it is to make them a much lower cost.
Very good. What frequency was the X20 data recorded?
I don't know exactly what the question is getting at, but the frame rate, I think, is, and when I showed that, one of the problems, and in retrospect, I probably shouldn't have shown the point cloud, is on screen shares and webinars, it depends on your download speed and latency of your link and so on. So the images look really herky-jerky. They look smooth on my end, and I don't know exactly. I think it was 20 frames per second. It might not have looked like that on your end, but that's because of the screen share rather than the data coming off of the X20.
Okay, I think we have time for a couple of more here. Some people are adding things in at the end. Where did that go? Are there any side lobes with this kind of beam steering? How do you solve that problem?
Oh, side lobes. Yes, there are side lobes. The way we solve that, there are two ways we solve that. On our short range LiDAR, the side lobes are not a problem because we synchronize the readout from the receive chip with the scan of the transmitter. And so we only read out the main lobe, so we merely ignore the side lobes. So it's not a problem in that architecture. In a long range architecture, we have steering LCM on both transmit and on receive. And in that case, side lobes do come into the main imaging chip in a way that can interfere with the main lobe. But we have some mathematical techniques, because the side lobes are very predictable. We have some mathematical techniques to eliminate them. So in the one architecture, it's a non-issue. In the other architecture, we use some signal processing to eliminate side lobes. Very
good. So I think we'll take this as the final one. We will get answers to everyone on these questions. So if you did not get your answer, it will be coming. What is the main difference from a conventional LCOS display?
So LCOS, or liquid crystal on silicon, is a technology that's been around for a long time. It's typically used for display technology in head-up displays and overhead projectors and that sort of thing. The main difference is we are not doing operation at visible wavelengths, and the way we modulate it is quite different in order to do beam steering. I mentioned liquid crystal on silicon because it's a conventional manufacturing technique, and we're essentially using that mature manufacturing technique, but applying it to a different way in which we modulate the reflection coming off of our chip. So think of it as same manufacturing process, different underlying modulation technique, and so we can do beam steering rather than forming images.
Very good. Alexis, Bill, thank you very much for a very informative webinar. Thank everyone for attending. If you could let us know what you think on the exit survey, we'd really appreciate it. And have a great day.
Thank you very much, everyone.
Thank you.